Today we're going to be covering compression settings. We're going to briefly cover a couple different types of compressors and then get into some applied techniques. Hello everyone and welcome to WaveSpot. My name is Austin Knaus and I've spent over 2 decades working with audio. My goal for this channel is to share all the fundamentals that I've learned along the way in hopes to give you a fast track to understanding the world of sound. So, let's dive in. So imagine this scenario. You're listening to a vocalist and they're whispering in their microphone. You turn the volume up to hear them better. And then all of a sudden they start yelling and now it's really loud. And so you rush to go turn the volume back down. Well, this is the job of a compressor. It prevents us from having to manually turn up and down the volume. It kind of does it on its own. And that's why they were originally created, to even out the dynamics of a sound. Whether it's really quiet or really loud, it brings them together, so there's not that big of a dynamic difference between the two. So if you're not too familiar with what dynamics are, you can check out this video up here. It'll cover everything you need to know and more about dynamics. Before we dive into the different settings of compressors, we need to understand that there are different types of compressors. The first being a voltage controlled amplifier, or a VCA compressor. A VCA, or a voltage controlled amplifier, uses voltage to control the amplification. The more voltage you apply, the more compression you get. VCA compressors are really fast. They're very accurate and they are transparent, meaning that they don't provide any coloration of your sound. So the only thing that happens is actual compression. VCA compressors typically have the attack, release, threshold, and ratio settings, and some of them actually have the knee setting, which we'll get into all of those here in a little bit. The next type of compressor is a FET compressor, or an FET, a field effect transistor compressor. Now, these mimic tube compression, but they're a lot faster and don't rely on actual tubes. These compressors do color your sound. They add harmonics, and they're actually quite aggressive. These are really good for guitars or vocals when you're going for a vintage style. The next type of compressor we have is an optical compressor, or an Opto compressor. Now, these use a light-dependent resistor and a light source on the inside to actually control the level of compression. These are a lot smoother, more organic sounding. One of the most infamous is the Teletronics LA2A. Now, this compressor only gives you the input gain and the peak reduction. So not a whole lot of control, but a whole lot of sound. Lastly, we have a variable mu compressor, or a tube compressor. Now these are very rich, warm, and lush sounding. One of the most infamous is the Fairchild 670. Due to the fact that a variable mu actually uses a tube inside, it's fairly slow when compared to something like a FET compressor. Now, this doesn't make it bad. This actually makes it a lot better for things like mastering, orchestral music, and bass lines. It's a lot smoother, richer, it's warm, it's colored by the tube. So now you can see the difference in compressors are really the internal electronic components that they're comprised of. Now, this gets into the debate of analog versus digital, which we're not going to get into today, but the characters of each compressor are defined by the components that they use. So without getting too far into the weeds, let's dive in and take a look at some different settings that we have at our disposal when we're using compressors. So if you remember our lesson on equalizers, we made this loop. Now this loop doesn't have any compression to it whatsoever, but in order for us to understand exactly what a compressor does, we're going to focus on this kick drum. The reason why is because it is a transient. A transient meaning it is a very quick sound. So here we're going to use FabFilter Pro C2, or Pro Compressor number 2. We're also going to take a look at it through an oscilloscope, which shows us our waveform. So this is the shape of our kick drum. An oscilloscope shows us the actual waveform instead of a frequency spectrum like span does. With both of these, this will allow us to actually see what's going on, because compressors can sometimes be hard to hear and hard to actually tell what's going on. So the first thing that we're going to talk about is the threshold. So what does the threshold do? Well, if you can see on this side of the compressor, we have dB. We have our volume level. And right now, our kick goes all the way up to 0 dB. Goes right up there to the top. So what our threshold does is it's a question of at what point do I want my compressor to start working? Well, if we go to -14 dB, we can see that it sets it at -14. We now have a line here. So let's play our kick drum and see what happens. We can see it starts to compress with this red line at that -14 mark. If we pull it down, we get more compression. And you can see that our kick drum over here is now kind of squashed. So our threshold is at what point does the compressor start working? The next thing is the ratio. Now the ratio tends to be something that is kind of tricky to think about, but we're going to simplify it really quick. So if we have a ratio of 1 to 1, that means for every 1 dB that passes our threshold, 1 dB is let through. If we have a ratio of 2 to 1, that means for every 2 dB that passes the threshold, only 1 dB is let through. So some quick math here. If we know that our original audio signal, or our kick drum, hit 0 dB at its peak, and we set the threshold to -14, how many dB past the threshold are we? Well, in this case, we're 14 dB past the threshold because our kick drum originally hit 0. So if we have a ratio of 2 to 1, that means that we can divide 14 by 2. So 14 divided by 2 is 7. So that means that the compressor is allowing 7 dB to pass through, which means that our new peak is actually 7 dB. And you can see we have our -6 line right here, and the compressor, the red line, shows us roughly that. So what if we did a 4 to 1 ratio? Well, if our original signal hit 0 dB and we set the threshold to -14, that means that our signal is 14 dB over the threshold. And if we have a ratio of 4 to 1, then we can divide 14 dB, which is 14 dB over the threshold, divide that by 4, and we get 3.5. This means that we're only letting 3.5 dB through the compressor. It's preventing the rest of it from passing through. Well, this would leave us at around -10.5. So -14 plus 3.5 is -10.5 dB. And if we look at our threshold and our compression rate, we're roughly around there. We can see between the -6 and -12 mark, it's right around where we're at. So now what if we did a ratio of 100 to 1? Well, we know that our original signal was at 0 dB, and we have a threshold of -14, which means our signal is moving 14 dB past the threshold. Well, if we take 14 dB divided by 100, then we're left with 0.14. So we're only letting 0.14 dB pass. This means that if we add 0.14 dB to our -14 dB threshold, we're actually only getting -13.86. So if we look at our meter here, we'll see it's going to be roughly around -13.86. Before we move on to attack and release, I want to cover the knee really quick. And you can see that's this bend here. Now that we understand that the threshold is at what gain level does the compressor start compressing, and the ratio is by how much compression is added, the knee is how gradually the compression is added. With a hard knee, the compression is immediately added as soon as the threshold is met. So as we can see here, as soon as the audio passes the threshold, that's when the compression starts. If we move into a medium soft to medium hard knee, the compression is gradually added a little bit before the audio actually passes their threshold. So you can see it brings it down a little bit. So that threshold with a hard knee is right at the number that we set. We go into a medium knee and it starts to bring down that threshold to a lower number. Now if we go to a completely soft knee, then the compression starts way before the actual threshold. Now that we understand those settings, let's get into attack and release. Now, I have a different perspective than most audio engineers when it comes to the attack setting. Most audio engineers explain the attack setting as how quickly the compressor starts compressing. I like to think of the attack setting as how much time am I allowing the compressor before it starts compressing. Different perspective. Let me show you. So if we reduce the threshold to a very low one and increase the ratio as high as we can go, we'll smash this kick drum. So let's look at it before. And that's our full kick drum. Now let's smash it. So you can see the audio is pretty much gone now. So attack and release are time-based functions. They're both measured in milliseconds. Now some quick math. There's 60,000 milliseconds in 1 minute. Why is that important? Well, in music, we measure our time in BPM, or beats per minute. So in our case here, we're actually working with 115 beats per minute. So if we take 60,000 milliseconds divided by 115 beats per minute, we're actually left with 521.74 milliseconds, which is a quarter note or a beat. Now, our kick drum is actually 1/16. So if we divide that by 2 twice or by 4 once, we're actually left with 130.43 milliseconds. Now, why is this important? This is important because attack and release are time-based functions and measured in milliseconds. So if I know that my kick drum is actually 130 milliseconds long, and I use an attack time of 0.005 milliseconds, there's going to be absolutely no kick drum that escapes this compressor. As you can see here, we have an instantaneous drop in gain or an instantaneous rise in compression. So what happens if we actually increase our attack time to 65.22 milliseconds, which is 130 milliseconds divided in 2? We actually get the front half of that transient shows up and passes through our compressor. And you can see here that this line isn't just as immediate anymore. See how it goes straight down here, but if we increase it to 65.22, we have a little bit of our kick drum going through. If we increase it to 130.43, which is the exact length of our kick drum, we can see that almost all of our kick drum comes through before the compressor actually reaches its peak compression. But it doesn't actually reach its peak compression because it doesn't have enough time to react. Remember, our threshold is at -60. And with an attack time of 130, which is the whole length of our kick drum, it's actually only reducing it by 42 dB. It's not actually reaching that full 60 mark that we told it to go to. If we increase this as far as it can go, the peak compression doesn't actually start until the kick is pretty much over. We can see here that it's actually only reducing by 33 dB, which is half of the amount that it should be. It should actually be a full 60 because that's where we told the threshold to start. But it's taking so long for the compressor to act, it's actually just kind of moving through it. It's escaping. So the attack isn't necessarily how quickly the compressor starts. It's how long of a time frame do you give the compressor to actually start working. With that being said, let's get into the release time. So the release time is kind of the opposite. I like to think of the release time as how long does it take to reset the compressor back to its zero state, back to the compressor being off. So if we set the compressor back to, let's do that 65.22 attack, so we have a little bit of that transient coming through, and we have a release time of 10 milliseconds, we can see that 10 milliseconds after the audio falls below the threshold, the compressor starts rising back up again. So we see this very quick U shape right here. Now, if we have an extremely long release time, this can prevent our kick drum from happening again because it takes too long for the compressor to reset. So let's take a look at what that would sound like. If we increase this, so we can see our transient here. So let's increase this. And as we increase the release time, making it a longer period of time, we can see that this U shape is now almost just flat lines. We don't even see our kick anymore. It's taking too long for the compressor to release itself. So this prevents the compressor from actually making it back to zero. You can see this compression rate is just staying there. If we go back to a shorter release time, you'll see the volume or the gain reduction here go back to zero very quickly. So if we release the kick drum all the way and we go back to no compression at all, we can see here that the peak happens around this 2 mark and the loudest bit of the bass is around this 4 mark. And the transient, or the initial spike of the kick drum, which is mimicking like the beater on the kick drum, is quite a bit lower than the actual sub of the bass. Well, what we can do is we can reshape the dynamics of this kick drum by using a compressor. So let's reshape this compressor, or reshape this kick drum using compression. So we'll start with a ratio of 2 to 1. We'll start with a fairly quick attack time at 0.25 milliseconds and a release time of, let's go with 100 milliseconds. And let's reduce the threshold from 0 down until we actually start applying some compression. Okay, so around, let's make this a whole number and do -15. So we can see that our kick drum still roughly has the same shape as when we started, it's just a little bit quieter. Let's manipulate some of these settings while keeping the threshold and the ratio the same. Let's mess with the knee, attack, and release time to see if we can get this initial transient to be louder than this bass section over here. Okay, so we smoothed this out a little bit. Now it's a little bit more triangular, if you will. So this peak section isn't quieter than this bass section anymore. Now the most important thing we can do here is let's turn off the compressor and check what the gain level was before we started adjusting it. So let's go take a look at our kick drum. So it's at negative 1.18. Let's turn our compressor back on. And we can see that it's at 5.32. So we can go ahead and roughly take this output level and increase it by 4 dB, because that's kind of what we lost. So now we're at negative 1.32. So if we really wanted to do it, we can go 4.2. And now we're at that 1.1 mark again. So if we turn our compressor off, we're at 1.18. And if we turn our compressor back on, we're at 1.12. So that is compression with gain staging. So we can now turn our compressor on and off and see if it made it sound any better. Now it's a very, very, very slight difference, but there's now more punch and less bass. We have more bass when it's off, less punch. And when it's on, we have more punch and less bass. So now you should have a better understanding of how compressors work. The threshold sets the point of which the compressor starts compressing. The ratio is by how much does the compressor compress. The knee is how gradually does the compressor start compressing. The attack is at what point in time does the compressor start compressing. And the release is how long does it take for the compressor to stop compressing. There are so many different ways to actually use a compressor. It's actually really easy to also overuse compression and overuse a compressor. There should always be a reason why you are using a compressor. Don't just throw on a compressor because you think you should use one. Put on a compressor because there's a specific reason why you want to use it. If you found any of today's information valuable, leave a like and hit that subscribe button. If you learned something new, or if you still have any questions, leave a comment below and I'd be more than happy to answer the questions for you. If you want to read more on the topic, head over to wavespot.com, where I have much greater detailed information written in a blog post, along with a bunch of illustrations. It's like 30 pages long. And until next time, thanks for watching.